Today should be a little bit more, I won't say entertaining, but it should be practical, interesting. It might be a better word to use. Because a lot of what we talk about in this class is theory application. I mean, we look at actual examples, but the usefulness of the examples is questionable. And I don't think you guys are going to go home and create a program that keeps track of your ice cream or marshmallows or pancakes or any of the other various things that we have put in data structures over the semester. And I know that when we create examples in class, the purpose is to show you how the data structure works, but not necessarily to give you a useful application for it that you can see and interact with. Certainly we talk about when structures should be used, when they should be avoided, and that sort of thing. But I wanted to take the opportunity today to show you two games that use a variety of the data structures that we've talked about. We're going to look at a little bit of the code. We won't get into too much of the code because it gets, I won't say it gets complex because it's not really difficult code, but it's a lot of code. And in order to kind of fish through it, it would be a little bit cumbersome. So I'm going to try to highlight it and show you how it works and talk about how it works without getting into the code because it can be a lot. All right, so the first one that we're going to look at is not this one, but we're going to look at, go away. We're going to look at a game called Meld. I'm going to open up a script. So here's Meld. It is a puzzle game. Can you guys see this? Yep. It's kind of hard. We'll start a new game. The idea with Meld is that you're trying to, it's a puzzle game, and you are trying to create a continuous path of like-colored elements between the two sparkly things. Okay? This is first level. Very simple. You simply drag the blue one here to create a path. Okay? Make sense? So I'm going to play just the first few levels to give you an idea. You can drag this anywhere, and it creates the path, and then you move on to the second level. Now the first few levels kind of show you just how the game works and that sort of thing. So we'll get through that, and then I'll talk about what structures are used and how they're used, and then we'll take a look at the code. So you can stack light-colored elements on top of each other, and then you can drag them off. So now there's two. I can put it back to make 3 or 4, or we can unstack them. You can move, if you have a continuous path of light-colored elements, you can take it and move it through the entire set. If you look up in the top left, you can see that there's 6 different colors in the game, and now we get to combining colors. So normal color combining rules, red plus blue equals purple. So if you combine 1 red with 1 blue, you get 2 purple. Okay, and then you use those to complete. Again, blue and yellow make green. You can't combine, you can move the yellow, but you can't combine it with the green, but you can combine it with the blue to make green. Make sense? Everybody understand those? It gets massively more complicated than that. You've got a whole set of, we haven't gotten to the power-up section, but there's like 30 different power-ups and special tiles, and you can throw, what's that? Yeah, it's on Steam. There are comets that you can shoot at the board to blow up stuff. There's solar flares and meteors, and you get into blocked tile. There's like 400 levels or 200, I don't know, it's been a while. But it gets really complicated. Data structures. Okay, so there's a variety of data structures used in this game. The two that we're going to take a look at are a stack and a hash table. Okay, so the stack, you guys, when we complete a level, what is done is, remember the little sparklies that flash, that indicate the path? Let's take a look at those. So if you have 3 reds and 2 yellows, you can't combine them because it's not equal. It has to be the same number. So 3 and 3 or 2 and 2. And so what I'm going to do is I'm going to pull off one of the reds, and then I can combine them. All right, so we'll combine the 2 here. So notice the particle effects that show. See the little white? So in game design, the creation of those graphics is expensive. And so a lot of times what is done is those are pre-cached, or those are created ahead of time, and then they're simply reused. Okay, and so the way the game works is, I actually, when the game first starts, I create like 15 of them. Okay, and I take them and I put them in a stack. And then whenever I need one, I simply pop one off of the stack, put it where I want it, and I wrote code that when it's finished playing its little effect, and I think I just do it after 2 seconds, it will take itself and put it back on the stack. Okay? Each graphic has a reference to the home stack, and when it's finished playing, it simply adds itself back to the stack. And so what happens is, it's possible that when you do a level, you might have a final path that's like 60 spots long. Okay? And so I don't want to have to create 60 of those little particle effect graphics. And so they actually just get reused. So I did the math and I just watched. By the time, if I'm creating a really long chain of graphics like that, I take the first one and I put it on the game board, and it plays its particle effect, and then the next one goes, and the next one goes, and the next one goes. By the time the first one is finished, it adds itself back onto the stack by the time the 16th one gets there. Okay? So the first 15 play, and then by the time it goes to request the 16th one, the first one has finished playing and added itself back to the stack, so I just pull it off the stack again and put it in the next spot. For the 17th one, the second one's done. So I just reuse them. And the stack works really nice because all of the particle effects are exactly the same. I just grab the next one off, and when I'm done, I throw it back onto the stack. Okay, does this make sense? So this is a practical example, very brief example of how that works. Okay. So any questions on that? Okay. Now, let's talk about the next one, because the next one is more complicated. So while the game is running, so if I go and I drag this one here, that'll complete the level, okay? But so if I drag this one, move it here, that'll complete the level because we have a continuous path up and around, right? But we have this extra tile down here that's not needed. And so the way the game actually checks to see if you've completed a level is by running an algorithm called A*. An A* is a pathfinding algorithm. You see it a lot in video games where you have a character and you want them to move from one spot to another and avoiding obstacles. Okay, there's show you a really basic example. Here's an old example of A star. So if you're this yellow dot and you can't walk on these round barrel areas, and I wanted to move right here, find the shortest path to get there. So I click there and it'll find the shortest path, avoiding the barrels. Okay? If I want to move down here, it'll find the shortest path. So this is the A star algorithm. This is interesting to you. This is one of the things that's covered in Intro to AI, or AI for Games. We spend a lot of time talking about A star. Okay? So I actually use a modified version of A star in Meld to check to see if you've successfully completed the level. Okay? Instead of checking for obstacles, I only check, or I basically assume, that any color that is not the color of the path is an obstacle. And at any point in time, if you have a valid path from here to here, then you've completed the level. And so what happens is, as it goes through, it finds this path, and because there's nowhere else to go from here, it just stops and assumes, okay, you haven't finished the level yet. But as soon as I take this and drag it up here, now I can complete the path all the way through. And A star, if it's done right, will find the shortest path. The shortest path will exclude this guy, because I can get there. If I move this guy here, I can get there just by going down like this. Okay? So, how does hash tables fit into this? Well, A star, in order to make it work, requires the use of two different lists. Okay? While the A star algorithm is running, it requires the use of two lists. One list, which is called the open list, keeps track of all of the available moves that you can make. All right, so when we start, the only available move I can make from here is here. Okay? Now, if I'm completely surrounded by green tiles, I could move to any of those. So when I am here, it would add all of the available places that I can move from here. It would add all of those to the open list. And as I go through, I'm going to continually add new things to the open list. Okay? Now, the way it selects what the best move is by assigning values to each of these spots. Now, we're not going to get into where those numbers or how those values are determined. Okay? But suffice to say, the lower the value, the better. So what we are interested in is each step or each iteration of the algorithm as it runs through figuring out where you should go. It constantly moves to the best position from what's available. Based off of what you know, think about all the data structures that we've talked about. What data structure should be used if you are interested only in the lowest value in a set of objects? Heap. What kind of heap? Min or max? Min heap. That's exactly what is used. We use a min heap to keep track of the open list. The second list that A star uses keeps track of all of the spaces, all of the tiles, all of the nodes, same thing. Keeps track of all of the tiles that you have visited. Okay, so as you're running the search, it keeps track of all the ones you've been to so that you don't go back there. You don't get like in loops in your search. Okay? That uses a hash table. And that's what we're going to look at in code today. So what it does is it keeps track of all of the nodes in a big hash table. Now, hash table works well because we can predict the maximum number of tiles that would go into the hash table, and it's simply how big the board can be. Okay. So let's take a look at that code. Here is the code. Now, this is C#. It's similar to, but not identical to Java, which is what we've been doing. Can you guys see this? I know it's don't exactly have the highest quality projector. Look at the top. There's an array of what? Array of tiles. Good. A tile is actually a script. Okay, so what we're actually doing is we're keeping an array of the scripts that are on each of the tiles so that we have access to information about the tile. And each one of the hexagons that we see is a tile. Make sense? So how big is our hash table? Here. So it goes from 0 to 186. So 187. Where do we think 187 comes from? If you had to guess. Just sound like a good number. Just pick it. Roll dice. Where do you think 187 comes from? There you go. Maximum number of possible tiles. I don't know what the dimensions of the board is. It's like 11 by something. But if we counted them, it starts like here and it goes all the way out to here, all the way down here, something like that. But that's the bounds of our hash table. Now, 187 is kind of a strange number. Let me just make it 200. And we talked about in class the relationship between making the array larger than it needs to be and the effect that has on collision and collision handling. So why do you think I used 187 instead of like 300? Why not make the array bigger than it needs to be?
Wasting memory or wasting...
Absolutely. It's a waste. Won't that have an effect on collision, though? Go ahead, just take guesses.
Looking at the hash function, it looks like you might have a way to just ensure that there won't be collisions.
Bingo. This is what's called a perfect hash table. Not because I coded it, but because there's a way to set up the hash function where there is no collision. Therefore, like you said, having additional spaces in the array is a waste. Now, you looked at this code, and you've never seen this code before, unless you hacked me, but how did you come to the determination that it looked like there was no collision?
Looking at you, it looks like you have X and Y for coordinates, and so you based it on just the coordinates of the tiles.
Absolutely. So here's the add method. We pass in a tile. If we look at this code, we are taking, so our hash table is the array, and we are adding to the array hash. So this gives us the index, and we're putting that position the tile that we want to add. Okay? So this is our array. This is the index of the array. The index of the array is returned by the hash function, and in that index we are putting the tile. Now, our hash function, we know, don't look at this code, what does the hash function get passed? What do we pass to the hash function? Generically speaking, you said it. The key. What is the key in hash tables? It's a unique identifier for an object. And we know that you take the key, you pass it to the hash function returns the index of where you should put that object in the array. Which is exactly what we have here. The hash function returns an int, which corresponds to the index where we put the object. Okay? Now, in some situations, the key is not a single variable, like in this case. In this case, it's a combination of two. There is no other tile in the program that has the same x and y values as another. They're all unique. And so we can take advantage of the fact that we have unique x and y values and come up with a number that is unique. And because the number is unique, we therefore don't have to deal with collision, right? Which makes it really simple. This is a coded from scratch data structure, and it's what, 29 lines of code? Not long. Questions on this? All right, let's do it. Now, here's another example. We're going to take another look at hash tables, but this is a built-in version of a hash table. We talked before about the announcing system and how it uses last names stored in a hash table. So, let's take a look at this. So I've set up just a really brief example here. So if you press X, this is just for testing purposes. If you press X while the game is running, it calls a function that says play player name from the announcer. Okay? Don't worry about those. Okay? And so what it does is these are just some parameters that specify how it should play it. But the idea here is that it takes what team am I? Takes the guy at position 0 of your roster, and it plays his last name. Now, if it has a last name, it will play it. If it doesn't have a last name, it defaults to playing the guy's number. Let's take a look at that code real quick. All right? So this is in announcer audio. We have play, player, name. Here's the code. You can see there's the parameters that are passed in. It's on the user's team, index on team, and how you play it. Okay? So this basically grabs the team data, whether you're the user or the computer. So we grab the last name, grab the audio clip. So what this does is this is what is responsible for actually pulling it out of the hash table. We'll look at that in just a second. If it doesn't equal null, meaning it actually pulled something out of there, then we will add it to the queue, commentary.add segment to queue, or we will simply play their number. So if we didn't find their name doesn't exist. If their name is last name of like something obscure like bubblegum, we don't have that in our audio database. And then we'll default to just playing their number. So if we look, what's this guy's last name? Jones? Probably safe to say that we've got Jones in our database. You hear that? Joe. Give me another name.
I like Hans Hogan.
Hans Hogan.
Number 13. Was it number 37?
37. Yes, it's
So give me a last name. Give me your last name. We'll see if your last name's in the game.
Hatfield.
Safidi.
Hatfield?
That is my last.
Let's see if your last name's in the game.
Nope.
I put it through the speakers in here, but our advanced technology only has VGA. I don't think it works. We could try it. I think it's been tried before.
Yeah, and that's what this probably doesn't have anything. I'm having it.
Or I broke it.
Yeah, that's kind of
really common name.
Can you hear it? I don't hear it.
That one. I will never do 4 classes work.
Definitely doesn't work. All right. defaulted to saying the guy's number. Okay? Sorry, we don't have Hatfield. Let's try another one.
Davidson.
Win. Davidson. That's a pretty common name. I bet we've got David.
So you highlighted it to put it in there? Or
I changed, so the way the game works is it reads that text file that I just had, and it populates the player statistics based off of what's in the text file. Like if we zoomed in,
No.
see it says Davidson on the back of his jersey now. You know what works? So it's a very moddable game. The idea, I can't say this. Be careful with that. So that's the way it works, and the idea is people could modify it. If you want to put yourself in the game, just simply change it. And there's an in-game interface that allows you to change this, because you open up the text file, you're like, ah. Yeah. But you can change anything from your skin color to your number to your height, your weight. This is a large. All the player attributes you can think of. Why are there so many asterisks? Come on, you're a computer scientist. You tell me what the asterisks are for.
You're the professor, you tell us.
You guys should know this. Why did I put those asterisks in there? Because it was pretty?
No.
It makes space.
What do you say?
No.
Null? Close.
Any possible value?
Nope.
is it because Atlanta has a star by it? So you can just star by everybody else?
Randomly fix it.
Yeah.
Separate values?
Separate values. It's delimiter.
Ah.
You can't do it based off of characters, because obviously there's going to be different lengths to each of the values. So the way it's coded is to split each line up based off of...
And Notepad's just screwing up the spacing.
Yeah. And that's why there's an in-game editor. I'll show you the code for reading the text file.
So how do you
I think it's like
But we want to do the line for this on class. Yeah, we're trying to get some service.
Right here.
Yeah, they should be doing this.
You hear my sleeves too?
It's right here. See how it splits it based off of the asterisk? All this does is it reads it in, it splits each line into an array, and then it splits each line into a set of strings based off of being split by the asterisk, and then it just returns the whole thing as a 2D array of shorts. So, let's look at the actual hash table. Now, this is the script for the announcer. Let me find it. There it is. So, when you, in C#, hash tables are called dictionaries. Okay, and you look at this code, it says, and we're in the announcer script class, private dictionary, last names. Now, inside of these angle brackets, we've seen these angle brackets before, right? With array lists. If we're doing an array list, what did we put inside of those angle brackets? Well, if you're going to declare an array list, you put private array list, name of your array list. What goes inside the angle bracket?
The data type.
Very good. the data type for the object that you're putting in there. And typically, well, with array lists, you have to use objects. And the type of an object is always the class you created from. Okay? So, if you look here, we actually have two things. And when you're dealing with hash tables or dictionaries, you're always going to see something called a KVP. Okay, a KVP. And what that stands for is a key value pair. And what it does is it identifies the key, which is a unique identifier, and then the value, what we're actually storing at that position. So if we relate this back to what we were talking about with MELD, the key was the XY, the value was the actual tile that we were storing in there. In this case, the key value pairing is a string and an audio clip. The audio clip is the actual last name. It's the guy saying Davidson inside of the brief MP3 or whatever. Okay? What value are we using to store? What is the key that we are using to store the audio clip? What does this say? You guys are so smart. Okay. So the idea here is we use a string to keep track of all of the audio clips. Okay. So if I wanted to find someone's audio clip for their last name, I would simply get their string that corresponds to their last name. So when we go back and look at the function, we say go play, player, name. When we actually pull it out, we call it get last name. Here is what is responsible for actually pulling the clip out of the dictionary. So name, it actually keeps track of their whole name. So substring, this basically strips out any other characters and just gives me the last name. Okay? Then I check to see if last names, which is the dictionary, contains the key name. Is it actually in there? If it is, then we'll store it. If not, well then this is just-in-time loading. This is so I don't have to load everybody's last name in there all at once. I simply create space for it, and then as it's requested, I check to see if it's already been loaded. If it's already been loaded, I just return it. If it hasn't been loaded, then I load it. But that's... Questions on this?